So, welcome everyone and welcome back. So, for the past couple of sessions, we've been looking at a lot of things involving triangles here. And triangles are great and all, but of course, there are other plane figures out there. Triangles are being the simplest of this sort of class of plane figures. And I think you know what I'm going to be talking about here. We're going to be looking at this idea of what are known as polygons here. Now, I mentioned the polygon at the very beginning of Unit 2 in our little chain of definitions here, but now we can actually go back, now that we understand what's going on, we can actually come up with a nice definition for this. So our definition for the polygon, we can mention, is a plane figure that is created by a closed path of line segments here. So something like this is going to occur where we have this sort of situation, and we kind of have this sort of thing here, right, with a closed figure. Most of the time when you're dealing with polygons, ladies and gentlemen, a lot of times when you think of polygons, you think about the number of sides here. So in this situation here, right, our triangle in this case, we have n equals 3, right? So here in this case, I'll let n be the number of sides. We can also have this sort of thing here, right? N equals 5 here, right? We can have a polygon like this where you have n equals 5. You can also have n equals, so I can just keep sketching here, n equals 8 here or something like that. So we can kind of sketch different polygons like this here. So notice how in this situation, ladies and gentlemen, we have this idea of polygons, and we can identify them by their sides. So you should know the prefixes for each of the polygons here, for 3 up to 12. So for instance, with 3 you have a triangle, with 4 you have a quadrilateral, then 5 you have a pentagon, 6 hexagon, 7 heptagon or septagon. Septagon both works here. 8 for octagon, 9 for nonagon, 10 for decagon, and 12 I think is another one that a lot of people know as dodecagon. Interestingly enough, your factoid of trivia here, ladies and gentlemen, is that you may notice that you've seen, septagon, octagon, nonagon, decagon. You may have seen these before, and that's if you look at the calendar months, right? September, October, November, December. So wait a minute, something's wrong here, right? Because sept, oct, non, deca is not 7 through 10, but for the years, September, October, November, December is not 7 through 10. It's 9 through 12. The reason for that is because of this no-name jerk back in the time of the Roman Empire known as Julius Caesar. He was the first to sort of really promulgate this idea of a new calendar, and he figured to himself, you know what? I'm so great. I'm an awesome guy. I should have a month named after myself. So in the original calendar, September, October, November, December were indeed the 7th, 8th, 9th, and 10th months. But Julius Caesar thought, okay, I want a month named after myself. So he inserted this month that he called July, and he stuck it in the summer because summer in the northern hemisphere has the longest amount of daylight, so you can do the most things. So because he was so important and things like that. So that got pushed everything back one. So then his successor by the name of Augustus Caesar came along and figured, you know what? My mentor, he was so great. He was important here. He had a month named after him. So I might as well have a month named after myself as well. And as a result, we have August, and that also pushed everything back. So as a result, unfortunately, September through December don't follow our standard naming conventions because of some two very, very rather self-centered individuals. But I digress. Okay, so notice how in this situation here, right? So here's n equals 5. Let's take a look at this one here. There are other kinds of polygons like this that you can draw where n equals 5. So something like this here. Chances are, if I ask you to draw also, you can have something that looks like this here. Here's n equals 5, right? You can think of this as a house or like home plate. But also, you can consider this here. Here, this is another pentagon. All of these are pentagons here, but this one, if you take a look at this, chances are if I asked you to draw a pentagon, you probably would not draw this, right? Because it doesn't seem very, I don't know, there's something about it. Aesthetically, it doesn't feel as good. It feels like, there's something missing. It feels like somebody did some surgery here and excised a large chunk of what used to be here. So these polygons here, you can see this one is a lot different from the other two here, and unfortunately that doesn't work out so well. So we refer to these here, we have these two types of polygons here. So this polygon here and this polygon here are its own group, and this polygon on the bottom is its own group as well. So we define this as what is known as convex. So we can say here, a polygon is convex if and only if a line segment connecting any 2 points on or within the polygon lies completely within the polygon. So basically it's saying that the polygon is kind of swells outward, so it's vaguely circular in nature. It doesn't sort of fold in on itself. And we refer to non-convex polygons or concave polygons if and only if it's not convex. So as an example here, again, I'm going to come back to this. As an example here, we can see that something like this here, right? Something like this, we can draw something like this here. No matter what 2 points I pick inside my polygon here, we kind of have this sort of thing where that line segment remains on the inside. However, over here, we can pick 2 points. So for instance, I can pick point A here and point B here, and this line segment that connects them, some of it's outside the polygon here. So we refer to that as non-convex. Most of the time, we will deal with convex polygons, ladies and gentlemen, so you don't have to worry too much about that here. But just to be on the safe side, you will, and I'm introducing you to this idea of non-convex polygons as well. So, based on this, this actually tells us a couple things here. So, what we have here is that there's some consequences of this definition here. A couple consequences. One consequence is that each interior angle of a convex polygon will measure less than 180 degrees. That's going to be really important here. So, because of the way it's set up here, every anterior angle won't be less than 180. In addition, a non-convex polygon will always contain at least one reflex angle here. So going back to our picture that we had before, this picture, we seem to have a reflex angle. As you can see, this reflex angle is inside our polygon like this. There's going to be one angle in the interior. It's always going to be greater than 180 degrees. And that's, again, part of the consequence of the definition here. So keep those things in mind. 3 last things here I want to talk about before we move on to the last part here. Note that we talked about equiangular and equilateral before when it came to triangles in the past. We can apply that definition to these polygons here. So we can talk about equiangular polygons. So it's a polygon where all the interior angles are congruent, right? And we can talk about equilateral polygons such as, well, in this case, where if and only if all the sides are congruent here. So notice that as you gain complexity, as you gain the number of sides here, equiangular and equilateral polygons here don't necessarily have to be hand in hand. You can have equiangular polygons that are not equilateral. You can have equilateral polygons that are not equiangular. But the ones that are both, we refer to these as regular polygons, if and only if they're equilateral and equiangular here. So if the polygon has this sort of thing here, these properties together, then we can kind of put this together and say, okay, this is a regular polygon here. Okay. Now, note that I mentioned before, we talked about this idea of number of sides for a polygon here, right? So in this case, we had our chart, right, for 3 through 12 here, and you should know those. But there, we can actually continue our naming convention. There is a way to name polygons that are more than 12 sides here. So you can have something like a triacanta pentagon. This here, you can actually look up triacanta pentagon. So this here, we see a 3 here. Canta really means times 10, and penta means 5 here. So this really means 30-sided polygon here. Now, since no one really knows this stuff, this is kind of the stuff that you would pick up from reading Wikipedia at random, or if you're studying to go on Jeopardy or something. In this case here, you don't need to know something like this here. If we have a polygon that has some number of sides, we can actually just call it a 35-gon. And we don't have to memorize the name triacanta pentagon here. 35-gon will suffice. And of course, if we have an n-sided polygon, we'll call it an n-gon here. So n-gon here just represents n sides. So in this situation, we can kind of say a hexagon is really a 6-gon. But we can also talk about other kinds of polygons out there, such as, a 27-gon or a 31-gon or a 99-gon, for instance. We can use that to calculate what's going on here. Okay.